Okay, guys, can you guys hear me? Hey, guys, can you guys hear me? Test, test. All right, so let's give it one more minute while we're receiving more students. Today is the first lecture of our session. We might have some technical issues for new students, have no idea how to log into our system, so on and so forth. So let's wait for one more minute before we get started. Okay. All right, it's 7:02, so let's get started. Hey, welcome, guys. Welcome to our North American Math Competition knowledge-based lectures. I know some of you guys maybe went to our bootcamp lectures. So the difference between two series, the bootcamp lectures will be more kind of like a quick going through, right? Go through all the topics in only 10 lectures. Well, on the other hand, our knowledge-based lectures is more focused on a specific topic. We might use like a full session, 10 lectures, talking about one or two specific topics. So that being said, give you more exposure, more immersion to a specific topic. In this session, we're going to go for session 3, 2D geometry. So I think geometry, like most of the students, they learn geometry, they learn algebra for a long time. So generally speaking, I have to say people are more familiar to algebra versus geometry. Why? Because I think about it, when you guys went to the kindergarten, you started your math journey by counting numbers, right? You know the numbers, you know like the basic adding, subtraction, so on and so forth. So everyone has a better understanding for algebra because algebra is more like with us forever. Well, on the other hand, the geometry, most of the students do not like geometry too much. Part of the reason is because we do not have a lot of exposure to geometry. We learn geometry way later than we learned the algebra for sure. And also, on the other hand, I think also from the teacher's perspective, especially when you come from North America, American schools or like the Canadian schools, you know what, like in the 1970s, around like 1970s, they actually paused the algebra education for a long time. By the time then in 70s and 80s, they basically focused on the algebra. They didn't really teach you like the geometry for too much, almost like for 2 decades. So that being said, even for most of the teacher, they're from being familiar to algebra is much better than being familiar to geometry. So this is more like systematic reason, right? From all over the places. So that being said, most of these students, they do not really like geometry. They think geometry is more like a killer. Okay. So think about it, just like, like Simon Cowell in American Got Talent. No one likes him. But on the other hand, these days, I have to say, in the North American math competition, the focus on the geometry is getting more and more. If you do some quick analysis statistics, you can find out, not to say the AMC, even the Canadian math competition, the Euclid, the COMC, like most of the math competitions, if you really count all the problems from different topics one by one, you can find out geometry is actually taking more than 35%. Okay, if you cut all the problem one by one, more than 35% of the topics of the problems are actually testing geometry. So that being said, have a good understanding to geometry will be crucial if you want to have a good score from the North American math competition. Okay, so that being said, we have to learn geometry. We have to give you guys a very good walking through about all the topics in geometry. So before we went to, just before we go to the details, the big topics here and there, let's have like an overall, kind of like an overall understanding. If I ask you the geometry problem that you have ever seen, I think generally speaking, we're looking at 3 major topics. Geometry is basically asking you 3 major topics. The first one is basically ask you to basically measurement a segment and its length. Think about it, recall all the all the geometry problem you have seen so far. It's basically a big chunk of problem is basically asking you the segment. Try to calculate the segment length, or maybe doing some quick proof about a segment, so on and so forth, right? The other part is angle, right? Some angle related either measurement or try to do some proof, so on and so forth. It's basically focused on the angle. And also another part is actually the area. Also, another part is actually calculating the area. Let's try to think about it from a, from math competitions perspective, to be honest. They do not really test you too much about the segment and angle, especially for the calculation, because you can use a ruler, right? You can use a ruler or you can use your measurement, basically try to measure what is the angle, what is the segment. So that being said, especially from AMC, right? You can actually have everything inside, right? So that being said, that they may not really like you to test these too much because you can actually do the measurement using your measurement equipments. So that being said, actually, most of the time, they're trying to test you something, the area related, because you won't be able to measure the area right away, right? You have to do some calculation, so on and so forth. And also think about it. Actually, when you are calculating the area, there are so many ways that you can get involved, either the segment or the angle. So that being said, if the question tests you the area, it is also testing the segment and the angle at the same time. So that being said, long story short, in the North American math competition, they will focus more on the area versus the angle and the segment. Because when they're testing the area, they're testing the segment and the angle at the same time. Okay, so that being said, to have a very good understanding how to determine the area could be crucial, right? So that being said, for our lecture, we're going to get started talking about the area, how to determine the area of a triangle, of a quadrilateral, of a polygon, so on and so forth. And taking from there, we will be able to open our journey to the 2D geometry part. And moving forward, we're going to go to the congruency, we're going to go to the similarity, we're going to go to the different ratio theorems in the triangle and the polygon. We're going to go to different centers on the, on the triangle, so on and so forth. But that being said, everything I think will be elaborated from having the good understanding to the area. How to measure the area, how to determine the area of a given shape is actually considered to be the foundation before we go to all the following topics. All right, so that being said, as a quick start, in today's lecture and also in our next lecture, let's try to talk about the area method. Let's try to summarize the different ways and different theorems that you have to know in order to solve all the area-related problem in the North American math competition. All right, this is kind of like an introduction where we come from, why we like to discuss about a topic. All right, so let's go to our lecture number 1. Let's go to different ways to determine the area. Okay, different ways to determine the area. Okay, so like I said, in our math competition, we might be able to see some triangle, maybe a quadrilateral, or even complicated polygons, right? So how to determine the area for different shape, right? Okay, long story short, in our North American math competition, or even the entire geometry, triangle is actually a very important element, or we can say as a kind of like a prototype or something. All those complicated shapes, they're actually elaborated from triangle. Let's say your quadrilateral can be cut using two triangles. Your polygon, you might be able to cut it into different triangles as well. So that being said, if you have a very good understanding for the triangle, that will be beneficial for all those, polygon, quadrilateral related discussions. All right. So that being said, in this entire lecture, let's try to focus on the triangle. And then I'm going to show you how to elaborate from triangle into more complicated flowery shapes. All right. So that being said, let's focus on the triangle. Let's focus how to determine the area of a triangle. Area of a triangle. This is considered to be the foundation for our entire math competition. All right, so different ways. Let's do this one by one. Number one, we're going to use the basic definition. I have a triangle ABC, right? This is actually my C, my B, my A. This is HA, right? So the area of my triangle ABC will be equals to 1/2A times HA, B times HB, C times HC, right? As long as you know this, you can graduate from the junior kindergarten, right? So everyone knows that from their kindergarten. This is exactly so easy. Even though I give you acute triangle, so this formula works fine for the obtuse triangle, right triangle, so on and so forth. This is basic 101 stuff. Okay, if 101 is good, let's go to 102. We still have exactly the same thing. Okay, and I always use an acute triangle as a demonstration purpose, but you can use whatever triangle you like. C, this is B, this is A, right? So here I'm still having my HA. So this time, HA can be represented using other form. So what is HA? HA can be written as B times sine C, right? The sinus of C times B, that's going to be HA. Or alternatively, can be C times sine B, right? On the left, on the right, you have two ways to represent HA. So that being said, you will be able to change your original formula a little bit by using maybe sine C, sine B, so on and so forth. So triangle ABC can be written as 1/2A. What is HA? HA can be written as B sine C. What is HA? HA can also be written as C sine B, right? And similarly, you can use B times C times sine A. Okay, so that being said, a triangle's area can be calculated using the product of two sides and the sinusoid value of this included angle. The product of two sides times the sinusoid value of this included angle. So far, so good? Okay, as long as you know this, I think you can graduate from senior kindergarten, right? This is like so easy. You learn that from day one. All right, so easy. Let's continue. What else? Is there some other ways to determine the area of a given triangle? The third one is the famous Heron's formula, right? Heron's formula say what? As long as you got a triangle ABC, you know the three sizes of a triangle, A, B, C, okay? As long as you know the three sizes of a triangle, you'll be able to determine the area of the triangle right away. So you would define P as A plus B plus C divided by 2, okay? So triangle ABC's area is going to be what? P minus A, P minus B, P minus C. Does it make sense? These are so easy peasy stuff, right? Okay. So Heron's formula is actually very straightforward because normally speaking, you see, you want to know the height. Previously, you want to know the height or you want to know some of the angle, right? But using Heron's formula, there's no need. As long as you know the three sizes of a triangle, you can determine the area right away. So Heron's formula looks like so easy, so powerful. It's like so easy to basically calculate the area of a triangle, but it also has its disadvantages. I'll give an example. Let's say if you're looking at a triangle like this, I don't know, maybe 6, 7, 8. I don't know. I'll just basically give you 3 numbers. So to determine the area of this should be fairly straightforward, right? But if I give you something, the 3 sizes not so nice, I give you something like this. Under root 7, under root 11, under root 13. Okay, this is also good, right? Well, as long as you're looking at such a thing, if you want to use the Heron's formula, no problem, but you're going to be having something like this. P equals to root 7, root 11, root 13. And then your area is going to be, oh my God, that's going to be a pretty nasty number. P is going to have so many under root here, there, and then P minus A, minus B, minus C. So you can still do the calculation, but I bet the calculation will be very nasty. You're going to be looking at a bunch of weird under root things here and there, right? So using Heron's formula is still doable, but your calculation process can be extremely complicated. In that case, do you know what should I do? What should I do? I can still use Heron's formula for sure, but it's going to be so nasty. I have to do a lot of like under root, complicated under root calculations. That's going to kill me, right? In these circumstances, can I do something slightly straightforward rather than doing something so nasty? Do you guys notice? Can I have some feedbacks? In our lectures, we have a lot of interactions. You can just unmute yourself and talk to me right away. Or you like to talk. Or if you like to chat, you can privately chat with me. Yeah, who would like to say something? How to deal with this?
I want to see something.
Yeah, go ahead.
We can find the angle of C by doing the cosine law.
Ah, that's nice.
We use like the formula you have like above.
Did you guys follow Boolean? Right? You can find the cosine value of B, right? Using the cosine law. And then taking from there, from the cosine value of B, you can find the sine value of B, right? Because I don't really care, cosine is positive, negative. In my triangle, sine is always positive, right? Sine, as long as you're from 0 to pi, sine is always positive. So this is always positive. And then I'm going to be able to use 1 over BC sine A, or like whatever, AC sine B. I can do whatever I like. Is that right? Okay, that's a brilliant solution. Okay. So I do not directly using the creepy Heron's formula. I'm going to use a little bit work around in order to make it out. Some other ways. This is really nice solution, right? Some other ways. There is another way I think is also very important. I like to show you guys. We can call it the double Pythagorean theorem. What is the double Pythagorean theorem? I'm going to show you something like this. Like I said, I have this nasty under root 7, under root 11, under root 13, right? Okay, I'm going to make a height on my under root 13 or like whatever side you like to do. As long as I do the height, I'm going to say this part will be x. So this part is going to be 13 under root 13 minus x. Does it make sense? So that being said, I'm going to use the Pythagorean theorem on 2 sides of this 2 right triangles. One is this red one. The other one is this blue one. Okay, so these 2 right triangles, they're sharing the same one of the right leg, right? Like the one using the dash red. So I would be able to say something like this. Under root 7 perfect square minus x perfect square equals to under root 11 perfect square minus under root 13 minus x perfect square, right? Because I'm using the Pythagorean twice, left and right. As long as you're doing this, you see, even though you have some nasty under root thing, but this is going to be something like this, right? Does it make sense? 7 minus x squared, 11 minus 13 plus 2 root 13 x minus x squared. Here, then you would be able to calculate the value of x very quick. This is not a very complicated calculation. As long as you figure out the value of x, you can go to whatever triangle, the red one or the blue one, using a quick Pythagorean rule, you will be able to determine the height of under root 13. That will be under root 7 perfect square minus x perfect square, right? As long as you figure out the value of h under root 13, you can basically determine the area of this triangle right away. So what I'm trying to say is, in this way, even though you're not having your solution right away, Heron's formula give you the solution right away, but you have to do some weird, complicated calculation. However, using this double Pythagorean theorem, you do not have the answer right away. You have the x first, and then from the x, you have the height. From the height, you have the area. But most of the time, you're dealing with some fairly straightforward number calculation. It's not big, complicated calculation, right? So at the end of the day, you're actually saving a lot of time than using directly the Heron's formula. Okay? So that being said, as long as you know the three sizes of a triangle, not always use the Heron's formula, you can basically have a choice. Either use it or using the double Pythagorean theorem. Your choice, you try to do whatever is the most convenient for you, and you're good to go. So far, so good? Can I have some feedbacks? Are we all on the same page for this?
Yeah.
Yes or no?
Yeah.
Okay, perfect. If all good, let's continue. The number 4 one I want to talk about is the famous bisector theorem. Okay, what is a bisector theorem? Let's have a quick look. I'm going to have a line like this. Yeah, maybe I'm going to change the color to make it more straightforward. Yeah, that's a line like this. Triangle goes like here, I guess. Yep. Perfect. I have a triangle. My triangle is like A, B, C. Okay. So for this triangle, I'm actually making 2 bisectors. One is the angle BAC. I'm going to put it here. This time I'm going to change the color to red. Okay. So angle BAC is actually my internal angle, right? I'm going to make an angle bisector for that. Also, I'm going to make another angle bisector for the external angle. Okay, now I'm good. I'm going to have this is my P, this is my Q, this is my T. So AP is the bisector of angle BAC, right? And AQ is the bisector of my external angle of BAC, which is the angle CAT. So that being said, these 2 angles are the same. Well, these 2 angles are the same, right? Okay, if that's the case, let's have a quick look at it. What's going to happen? Okay, let's focus on the internal angle, the first one first. First thing first. Bisector of angle BAC. Bisector of angle BAC, I would focus on these 2 triangles. One is this red one. The other one is the blue one. Okay, this pretty slim triangles. If I want to determine the area ratio of these 2 triangles, ABP, APC. So for my ABP triangle is actually, I can use the second theorem I just introduced. The area of this triangle is 1/2 AB times AP times sine angle red, right? Sine angle red. And same thing, the lower one, 1/2 AP times AC times sine angle also red, right? Because it's an angle bisector. So the two angles have the same measurement. So let's have a quick look at it. Of course, this could be canceled. AP, they're sharing. 1/2 is canceled. So that being said, the value for this guy is going to be AB over AC, right? The red triangle and the blue triangle, the area ratio is AB over AC. But wait for a second, what's the area ratio between these two triangles? The red one and blue one, they're basically sharing the same height, right? But the bottom one is BP, the other one is PC. So they're sharing the same height. Once bottom is BP, the other bottom is PC. Using our method number one, the basic definition, what is the area of a triangle? So triangle ABP's area over triangle APC's area can also be written as 1/2 BP times the height, PC times the height, which is BP over PC. Okay. The same thing, one is equals to AB over AC, the other one is equal to BP over PC. So that being said, I can consolidate these two terms together, right? So you're going to have what? AB over AC, BP over PC. Let me try to write it here. AB over AC, BP over PC. Okay, so you have such a relationship. So as long as AP is an angle bisector of a given triangle, so the two sides ratio, AB over AC, is actually the same as the two segment which was cut by the angle bisector, right? The ratio between those two segments, BP over PC. Okay, this is the conclusion that we want to have. We give a name. This is the internal angle bisector theorem. Internal angle bisector theorem. I think this is quite understandable, right? So trust me, angle bisector theorem should be your number one reaction as long as you see the condition angle bisector. Previously, when we say, as long as you see like an angle bisector, you're going to see like two angles are the same. But these days, AMC is no longer testing it. Your first reaction, as long as you see the angle bisector, there must be the ratio between the two sizes will be the same as the ratio between the two segments, which was cut by the angle bisector. This is extremely important. Try to remember this. Okay? So this is what we call internal angle bisector theorem. Now, what about external, right? We say internal, we're probably talking about external as well. So external, how it works. I'm going to check the other two triangles. One is triangle ABQ, the black one, the big one, the black one. Okay, I'm going to write it here. The other one is ACQ. ACQ is the yellow one. The yellow one, I want to make it here. Let's try to determine the area ratio between these two guys. The black one, the big one, and the yellow one, ACQ. I'm going to write it here to make it more straightforward for you to do. Triangle ABQ over triangle ACQ will be using what? 1/2 ABQ. ABQ is what? ABQ is actually AB times AQ sine BAQ, right? It's the big one, sine BAQ. And what about the lower one? The lower one is ACQ. ACQ is 1/2 AC AQ sine CAQ. Let's have a look about these two guys. One is BAQ. BAQ is this big one, right? The other one is CAQ. CAQ is here. Well, because AQ is actually what? It's an angle bisector for angle CAT. So therefore, these two guys are the same. Angle CAQ is the same as angle EAQ, right? So I can basically replace it using angle TAQ. Now let's have a look at it. Angle TAQ is here, and angle BAQ is here. So what's the relationship between TAQ and BAQ? Adding them together equals to 180 degrees. If two angles, they are supplementary, right? Adding them together equals to 180 degrees. So what's the relationship between the sinusoid value? Who can tell me? If two angles, adding them together equals to 180 degrees, then what's the relationship between the sinusoid value? Paul?
They're equal.
They're equal to each other, right? Because alpha plus beta equals to pi. So sine alpha equals to sine beta, right? So this is more like a trigonometry. It's slightly outside the scope of our current session, but I think this is something so easy, so everyone should know that, right? So that being said, these two guys could be canceled, right? Same thing, AQ could be canceled. So the ratio between these two guys is going to be AB over AC. AB over AC. And also, similarly, what's the area ratio between angle ABQ, the black one, and angle ACQ, the yellow one? They're sharing the same height. So the area ratio could be the bottom ratio, right? On the other side, this could be BQ over QC. This is quite understandable, right? So I'm going to do exactly the same thing as we did for the internal angle theorem. I'm going to give you external angle theorem. AB over AC equals to BQ over QC. AB over AC, BQ over QC. So this is what we call external angle bisector theorem. Okay? External angle bisector theorem. If you do a comparison between the internal one and the external one, you actually find out they're essentially talking about the same thing. So let's have a quick look. Internal one is AB over AC equals to BP to PC. What is P? P is actually the intersection between the angle bisector and our BC segment, right? And the lower one is AB over AC equals to BQ over QC. What is Q? Q is also intersection, but it is the intersection between the external angles bisector to the bottom, right? It's actually, of course, in the extension of BC. So that being said, actually the angle bisectors, internal one or external one, they're essentially talking about the same thing. It's always something like this. Side A, over side B equals to what? Side A, this is A, this is B, equals to what? A to the intersection point, and then intersection point to B. Is that right? So as long as you find the intersection point, my A side over B side is always from here to the intersection, and then the intersection back to the other endpoints. Or even though you go to the external one, it doesn't matter, from here to the intersection, and then go back to the other segment endpoint. So that being said, you can easily consolidate or unify the external or internal angle bisector into one formula. From the very beginning to the intersection point, from the intersection point, go to the other endpoints. And then here is going to be side A over side B. So this is actually a very important formula I want you guys to remember when you're dealing with the angle bisector. Like I said, angle bisector these days is so important. The moment you see angle bisector, the moment you're going to choose the angle bisector theorem in order to solve the problem. Okay, so far so good. So these are the basic stuff. Okay, if all good, let's continue. Number 5, let's go to the famous sine law. Sine law is also very important. We're actually using it a lot. I have a triangle. I have 3 sizes, A, B, C, right? So you have A over sine A equals to B over sine B, C over sine C equals to 2R, right? What is this R? R is actually the radius of the circumcircle, right? R is the radius of the circumcircle. Okay, I think this is something so easy. Everyone pretty much know this for a long time. Okay, and also here I want to mention a very important thing as well, since we're talking about the circumcircle thing, right? I have any kind of triangle. The area of a triangle could be written as what? ABC over 4R. Is it right? You guys know this? If I wanted to determine the area of a given triangle and I know the radius of the circumcircle, okay, then the area of this triangle could be written as ABC over 4R. Do you guys know this? Can I have a quick survey? Do you guys know this? Yes or no? Okay, this is very important. Yeah, try to remember this. I think 1 year they actually used one of the AIME exam using this to expedite your calculation process. If you don't, no problem. This is very easy peasy calculation. You'll be able to do a quick proof. If you don't know, let me know. We can talk about it. I can give you some information offline, but I think most of the students telling me they know this. So let's try to move forward. Yeah, by the way, if I'm talking about some, because we have many students, we just want to make sure we're focused on the majority. But if you think some topics you don't really understand, you can't follow me, type with me privately. I'm going to be able to send you some extra information offline so you can still try to catch up with the other students. Okay. So this is actually, if I know the radius of the circumcircle of a given triangle, that way I will be easy to determine the area of the triangle. And then what about I know the yin circle's area, yin circle's radius? What's going to do? What is the area of my yin circle's radius? Do you guys know that? Right. So since we talk about the circumcircle, let's talk about some yin circle as well. If you know the yin circle's radius, there's also a very quick way for you to determine the area of the given triangle. Do you guys know that? S triangle could be equals to R times S. R is the radius of the yin circle. S is the semi-perimeter. You have the perimeter divided by 2, and then that's going to be your S. R times S is going to be the area of your given triangle. So far, so good? I think there's something quite understandable, right? Okay. So if all good, let's continue. We talk about a sine law, we have to talk about a cosine law right away, right? Sine law and cosine law are kind of like a twin brother. You know one, you automatically know the other. So cosine law is like this: A, B, C, A, B, C. So your cosine A will be B squared C squared minus A squared 2BC. Cosine B will be a squared c squared b squared to ac. Cosine c will be b squared a squared minus c squared to ab. Okay? So how to remember the cosine law? There's a very quick thing you can remember is you never get what you want. You never get what you want. If you want to determine cosine A, then you want to subtract cosine A. And in your denominator, there's no A. If you want to do the cosine B, you want to subtract B squared. And then in the denominator, there's no B. Same thing applies for the C, right? So like I said, like the shortcut to remember it, you never get what you want, right? It's like life. Life is also like this, right? So this is a quick way to remember the cosine law. So trust me, cosine law is actually way more important than sine law. Okay, there's so many math competitions, they test you a lot on the cosine law. Cosine law will be tested every single year, no exception. Sine law might not be that much as important as cosine law, right? But cosine law, trust me, American, Canadian math competition, they will test it every single year, no exception. Okay? And how to prove cosine law? You can actually try to Google it. It is not very complicated. You can try to Google the proof. It's actually using some Pythagorean theorem, you can actually prove the cosine law. But I think most of the time, you just take it, right? Even for our day school teachers, we just introduce this cosine law without giving you a lot of complicated proof. Okay. Number 6, after number 6, let's go to number 7. Let's go to the Pythagorean theorem. Pythagorean theorem is actually something so easy, right? There's nothing to say. This is A, this is B, this is C. As long as you have a right triangle, A squared plus B squared equals to C squared, right? This is kind of like a given, right? Pythagorean theorem, everyone know that from your I don't know, elementary school or something, right? Yeah, just one thing I want to have a very quick extension is Pythagorean theorem is actually for the right triangle, right? As long as the triangle is a right triangle, you have a squared and b squared, a squared plus b squared equals to c squared. So that being said, to connect a squared plus b squared, you use an equal sign, okay, to the c squared. Then what about my triangle is not a right triangle? What about I have a acute triangle? Or I have an obtuse triangle. Okay, I'm no longer having the, like the right triangle. I can have a acute triangle. I can have a obtuse triangle. It is all possible, right? So my question is that when you are having a right triangle, the operator connecting the a squared plus b squared and the c squared is equal. But as long as my triangle is no longer a right triangle, aka it becomes a acute triangle and obtuse triangle, what should I do to connect my two sizes? Who can tell me? Who can tell me? As long as I'm having a right triangle, of course I have my Pythagorean, that's no problem. But a quick extension is, if my triangle has been changed from a right triangle into an acute triangle into an obtuse triangle, of course the equal sign is no longer there for sure, right? So if this equal sign is no longer there, I still want to make a connection between the two sides. I'm probably going to use the larger or smaller, right? Lesser than or greater than, right? So which one would be greater than, which one should be lesser than? Let's start. I'm going to ask for Ethan. Ethan, can you talk?
Acute would be greater than obtuse would be less than.
That's perfect. Why? Can you do a very quick explanation?
Like acute would be if you like squeezed the from A and B, if you like squeezed C to be smaller, I guess. And then obtuse would just be if you stretch it to be bigger.
Is that right? That's a brilliant explanation. There's so many ways to understand it. One is using Ethan's method, squeeze them or scratch them. Or you can say in a triangle, you always have a larger angle will basically facing a larger side, right? The angle become larger, the side become larger. So as long as acute triangle, your angle C is become smaller. It used to be 90 degrees in right. Acute triangle should be lesser than 90. So therefore the C side will become smaller, right? Similarly, in the butte, like a obtuse triangle, your angle C becomes bigger, right? Bigger than 90 degrees. So therefore the facing side C will become bigger as well, right? So that being said, you'll be able to make the two sizes become smaller or bigger. This is one way. Or you can directly use the cosine law, right? Because cosine law directly use the B square, let's say if you want to go for this, right? If angle C becomes an obtuse triangle, so cosine C will be lesser than 0. If lesser than 0 means A square plus B square will be lesser than C square, right? So that will make sure cosine C will be negative. You see, all the knowledge are connected, right? As long as you know one, you can basically derive all the other things fairly quick. So far, so good. So this is our number 7, the Pythagorean theorem that everyone knows that. Let's go to number 8. Number 8 is the spread angle theorem. Spread angle theorem. What is that? It's going to be something like this. I have a triangle ABC. Okay. P is a dynamic point on the BC side. P is a dynamic point on BC. Okay. As long as you do the connection between AP, you basically generate two angles, which is alpha and beta, right? One is alpha, one is beta. Then automatically you should have sine alpha plus beta, which is my angle BAC, over AP. It's going to be equal to sine alpha over AC, sine beta over AP. Okay. Sine alpha plus beta is basically my angle BAC, right? My big angle. So this angle over AP can be written as sine alpha over, not AB, over AC. That's not the same side, right? It's opposite side, plus sine beta over AP. So this is more like a spread. So why do I have the name spread angle? Spread is more like, see, from the P point, you're going up, right? This is actually your spread, right? Basically, your entire angle BAC has been split into two parts. So this is more like a spread. So this is what I say, a spread angle. Okay. A spread angle formula actually mentioned that from this top angle BAC over the angle AP or over the segment AP can be written as the sum of one side alpha over the other side AC plus the other side alpha over the other side AP segment. How to prove this? How to prove this? Actually, the proving for this is fairly straightforward, very straightforward. We can actually do something like this. Because 1 over 2 AB AC times sine alpha plus beta. I'm going to be able to use the two angles sums trigonometry. 1 over 2 AB AP sine alpha cosine beta. 1 over 2 AP AC ABAC, yeah. ABAC. Cosine alpha sine beta. Okay, you just basically divide 1/2 AB, AC, AP, and then you're good to go. You just basically use one, like the sine alpha plus beta formula expanded and do some quick division, do some quick modifications for that, and then simplify, you'll be able to have what you need. This is fairly straightforward. I'll leave this as a homework. You can think about it. Okay. So this is actually what we call a spread angle formula. As long as you have triangle, you have a dynamic point on the PC. On the BC side, you generate a spread angle, that you have such a relationship. And this guy actually has a reverse theorem. So number 9, I'll say spread angle inverse theorem. What is the inverse angle theorem? It goes like this. Now, if I have an angle BAC, okay? I have a ray basically emanating from A. I have a ray emanating from A. And it basically cut into two parts, right? One is angle alpha, one is angle beta. Okay? As long as I can prove if there exists a point T such that sine alpha plus beta AT, sine alpha AC, sine beta AB. Let's say I have a point T here. I can make sure sine alpha plus beta over AT equals to sine alpha over AC plus sine alpha over AB. Then I can say BTC, the 3 points are actually collinear. Okay, so think about it. What's the relationship between number 8 theorem and number 9 theorem? Number 8 theorem is basically you have a triangle. You find a point on the BC side. Of course, BPC, the 3 points will be collinear, right? And then you have a spread angle property. Well, number 9 theorem says that you just have an angle and then you randomly find 3 points, BTC, as long as you can make sure A alpha sine alpha plus beta over AT equals sine alpha over AC plus sine beta over AB, then you can say that BTC, 3 points, are actually collinear. Because at the very beginning, there's no way, there's no guarantee that BTC, you just randomly find some points, right? There's no guarantee that 3 points are collinear. However, if you have the spread angle property exist, that condition is there, then you will be able to prove, okay, BTC, 3 points are actually collinear to each other. So far, so good. This is something very important. Please try to remember this. Okay, if all good, let's go to number 10. Number 10, let's go to the Stewart theorem. The very important Stewart theorem. So Stewart theorem, I think pretty much everyone already knows that. I'm just gonna do a quick summary. ABC, you have a point P, which is dynamic point on the BC side of triangle ABC. So I'll say given triangle ABC, P is a dynamic point on the BC side. Okay, then you will have AP square equals to AB square, PC over BC. AC square, BP over BC, BP square, PC, BC, BP, BC. Okay. What does a dynamic point means? Dynamic point means the point is just here. I mean, this point can be moving. You do not have to be P must be in the middle, or P must be a perpendicular foot, or P must be 1/3 of this entire segment. P can be moving. Whatever you want to put your P can be wherever. Okay? At the end of the day, you always have this theorem behold. So that's the definition for the dynamic point. Okay, so this is the Stewart theorem. Stewart theorem looks like so nasty, so ugly, right? You have like so many complicated things. And not to say how can I remember it, what does it mean, right? I mean, what's the meaningful of this? What is like the added value to know such a theorem? The added value of such a theorem says something like this. As long as you have a triangle, ABC, you find a point P on the BC side, then you have 1, 2, 3, 4, 5, right? 5 segment that you have in this triangle. So the Stewart theorem just say there's a relationship between this 5 segment. It cannot be random relationship, right? There must be a relationship between this 5 segment. So as long as you know 4, put it into this, plug in into this triangle, into this equation, you would be able to determine the 5th one, right? 5 segment, as long as you know 4 of them, you can determine the 5th one. Does it make sense? So that being said is, as long as you have a triangle like this, all the 5 segments, there's an internal relationship. As long as you have 4, the last one is like specifically determined. There's no way for you to put a random number for the last one, because there's 5 guys together, you have to plug in into this Stewart theorem, and you'll be able to find out an equation between them. Okay? But this is so nasty to remember the Stewart theorem. There's like, so many things. Is there a way for me to really help me to remember the Stewart theorem? Yes, there's a quick way to remember the Stewart theorem. So quick way, trick to remember. It's so complicated, right? You won't be able to remember such a big thing, but there's a quick way to remember it. I'm going to give it to you. So you have, this is A, B, C. So this is your C, B, D, M, N. So this is A, right? Pretty much the same thing. I just give you more like different denotation for this. Then automatically you have M, A, N, D, A, D, B, M, B, C, N, C. M segment times A segment times B segment plus DAD equals to BNB times CNC. So if you remembered it in the more English way, is a man and his dad put a bomb in the sink. A man and his dad put a bomb in the sink. Try to remember this. So this is going to help you to remember the Stewart theorem. Okay, Stewart theorem. All right. So Stewart theorem by any means is a little bit complicated, right? Sometimes even though you want to have this way to remember, you might have a hard time. Okay, if that's the case, you know what? Even though you can't remember the Stewart theorem, there are 3 exceptions I want you to remember. Stewart is a very generic solution, right? P can be wherever you like to be. But in some certain conditions, I want you to at least remember this. So here is going to be a quick extension. for Stewart. So first extension is when AP is a bisector. You see, AP is no longer a random segment, right? AP is actually angle bisector for BAC. So what's going to happen? A, B, P, C. As long as you have this, your complicated, nasty Stewart theorem would be further simplified into something like this. AP square equals to AB times AC minus BP times PC. AP square equals to AB times AC minus BP times PC. This is much easier, right, than the previous one. And this is the famous bisector length formula. Bisector length formula. As long as you have a bisector, the angle bisector, you'll be able to determine the length of this angle bisector simply using AB, AC, BP, BC. This is the number one thing. This is a more specific scenario, right? This is not a very generic way. It's more specific scenario. Second one. What about AP? AP is not a bisector, but when AP is the median. AP is the median of BC. What's going to happen? So this time it is not an angle bisector, but it's a median. Okay? You're going to have AP square equals to 1 over 2 AB square, 1 over 2 AC square, 1 over 4 BC square. Okay? This is the second one you need to remember. If you can't remember the Stewart, you have to remember this. Whenever AP is the median of your BC side, you still want to do this, your complicated Stewart theorem might be simplified into something like this. And also we give a name. This is the median length theorem. You see, we have the bisector length theorem. Now we have the median length theorem, which makes sense, right? And the third one you need to remember is, this time I'm not going to put something too special for the AP. AP can be whatever you like to be, but the triangle per se becomes a little bit special. So this time, when AP is equals to AC, so this is like what? This is like an isosceles triangle, right? Okay, I'm gonna. So this is isosceles triangle, A, B, C. But this time, like I said, since AB equals to AC, it's already very special. So my point P can be more casual. Your P can be whatever. As long as it's like moving along the BC, you're good. You're gonna have AB equals to AC. So P is dynamic. So you're gonna have AP square equals to AB square minus BP times PC. This is the third one. This is the third one. In the isosceles triangle, you find a dynamic point in the bottom. You do a connection, you automatically have such a relationship. So this identity is there all the time. So far, so good. So if you want to remember the Stewart theorem, that's perfect. If you can't remember, at least you know some special scenarios. The AP is angle bisector, AP is the median, or the triangle per se is an isosceles triangle. That's going to help you to at least remember the most important thing that you like to see. Okay, so far so good. If we're good, let's continue to the pretty much the last one. It's going to be our theorem number, let me see, number 11. Yeah, the last one is also fairly understandable as well. So as long as I have a quadrilateral, okay, in my quadrilateral A, B, C, oops, sorry. Okay, A, B, C, D. Okay, so this time the diagonal of my quadrilateral is actually perpendicular to each other. AC perpendicular to BD. So the area of my quadrilateral ABCD is going to be 1/2 BD times AC, right? The product of these two diagonals, and then take a half of them. That's going to be the area of this entire quadrilateral. Okay, quadrilateral. I think this is understandable as well, right? All right, so that's basically talking about the majority ways and the majority theorems that you need to know whenever you're dealing with the triangles, area, so on and so forth. And the last one, we talked something about this quadrilateral, but it doesn't matter. Quadrilateral is actually derived from triangle, right? You can basically split the quadrilateral into two triangles, and then you'll be able to solve the problem. So far, so good? All right. So this is basically all the theoretical theorems, theoretical tools that you can utilize in order to solve the triangles or quadrilateral or polygons area problem. But before we jump to the problems, so what are the generic rule, like the strategy, right? We always like to say the strategy. So what are the strategies that you want to deal with as long as you're dealing with the triangle problem, area problem, so on and so forth? I would say most of the area-related problem. At the very beginning, you want to try the definition. Definition is more like, using the bottom times the height, or using two sizes and this included angle, so on and so forth. This is your number one way to think about it. And most of the time, it didn't work, right? You won't be able to basically do this definition-related stuff. If the definition doesn't work, most of the time, you want to determine some ratio between different triangles. So what do I mean? So most of the time, whenever you see some complicated problems, I don't know, I just want to give an example. So you're triangle number 1, number 2, number 3. Most likely, you want to say these two triangles, they're sharing the same height. So the area ratio will be directly the bottom ratio. Does it right? The area always go to the bottom. Or if they share the same bottom, the area ratio would be the heights ratio, so on and so forth. The ratio one actually takes the majority of your calculation in the math competition. So this is one of them, using the, similar, they sharing the similar height, the similar bottom, so on and so forth. Or another very important one is using the similarity. Because similar triangles, their area ratio will be the similarity ratios perfect square, right? The area ratio would be the similarity ratios perfect square. Okay, I think everyone knows that. And the third one is also very common strategy is try to use the sine law or the cosine law. Of course, sine law is not that much important compared with cosine law. Most of the time, you're dealing with the cosine law. But generally speaking, using the sine law or cosine law would be able to help you do a lot of related stuff. And last but not least, if you really have no ways to solve them, you can think about something like the Heron's formula or like the Stewart theorem, so on and so forth. Some other more flowery, more fancy ways to determine the area. But you always want to get started sequentially. You want to start with the definition. This is your number one thing. Okay, even though it doesn't work all the time, but try to do it in the first time. Second, go for the ratio. They can be same bottom, same height, or can be simply similarities ratio. And then try to use some sine law, cosine law, trigonometry, some other ways to help you to determine the area in a more flowery way. Last but not least is try to use the Heron's formula. Heron's formula, or like the Stewart, or some derivations from Stewart, just give you more flowery ways to determine the area and taking from there. Okay, so these are all like the high level thing, how to determine the area and area ratio. So with all of this, plus all the technologies we introduced from the very beginning, let's see some real problems. Okay, let's go to our problems. Question number 1. Question number 1, there's a warm-up question. As shown in triangle ABC, EF is parallel to BC. Triangle AEF's area is the same as triangle BCD's area. If entire triangle ABC's area equals to 1, try to determine triangle CF's area. I'm going to give you the graph. Okay, I have a triangle A, B, C. My EF is parallel to BC. Okay, my triangle AEF has the same area as my triangle BCE. Okay, where's AEF? AEF is this blue one. It's the same area as this blue one, BCE. With all those information, try to determine the area of my triangle. Yeah, and also one more thing is entire triangle ABC has an area equals to 1. With all those information, try to determine the red part, red triangle's area. How can I deal with such a problem? Thinking process is always important, right? We're not talking about the solution. We're not reading the solutions for you. Let's try to think how we can do such a problem. So you see, you have a triangle, you have some EF is parallel to BC, okay? And then these two blue ones are equal to each other. The big one equals to 1. The question asks you to determine the small red one. So let's do this one by one. Can we use the definition? I don't think so, right? You don't really have the height. You don't really have the bottom. Number 1, pass. Number 2, can I use the ratio? Try to use some ratio of different triangles and hopefully solve the problem. Can I use the ratio? Who can tell me? Or any kind of like condition given by the problem hints you I can use ratio or I cannot use ratio. Ethan?
Like the parallel lines.
Is that right? That's a brilliant observation. As long as you see the parallel line, you automatically think about similarity or some lines that are cut into different ratio. There's some complicated ratio theorems that are all introduced by the parallel lines, right? So this is actually very important, what we call the conditional react. As long as you see this kind of the action word, a key word, then you will think about maybe I could use the ratio. Right? Ratio, like I said, there could be two triangles sharing the same bottom, the same height, or two triangles that are similar to each other. I don't know. Let's try to have a quick look. Well, the question, I think the question per se is fairly understandable. The question gives you through like a big triangle, area equals to 1, and then it is cut into 3 parts, 1 red parts, 2 blue parts. And the question asks you to determine the area of the red parts. So if you want me to determine the red part, maybe I'm going to put the red part equals to x. Okay, it doesn't matter. You just like whatever you want me to do, just try to do s. We let triangle ECF's area equals to x. If this is x, I think it's fairly easy for you to determine the area of the other two, because the other two are the same area and the total area is 1. So they're both 1 minus x divided by 2. Right? This is something quite understandable. Okay. Now think about it. I'm looking at a graph that only has one variable, x, right? So if I can construct an equation, just one equation, there's only one variable, one equation will be good enough, right? I just need one equation and then I'll be able to solve x, get my value. The $1 million question is, what this one equation looks like. How can I construct this one equation? I want to use some ratio to construct my one equation. Who can tell me? How can I use the ratio to make it work? One equation, good enough. Like I said, if you want to do the ratio, you have two ways, either using the height related stuff or using the similarity, right? I think for this problem, you're going to use them both. One side will be similarity ratio, one side will be the height ratio. Because you need to have an equal sign, connect two of them, right? They must be connected. Who have some idea? Who has some ideas? Paul?
Maybe you could use like the heights of the triangles to try and get a relationship.
Okay, yes, yes. What can you do for that? You want to elaborate? Who can elaborate a little bit more?
So maybe you have like the height from like A to like EF be like H1 and like the length from like EF to BC be like H2 and try to find some ratio with like the areas.
Okay, okay. Yeah. That's a good way. But let me give you a quick hint. You already see a EF equals to BC condition. If I want to use the similarity, what can you get right away? Think about it. As long as this is what we're going to talk about it in our similarity section for sure. As long as you see two triangles, AE, like the AEF, like the top blue one, and the entire ABC, they're similar to each other, right? We always say that similarities ratio will be the area. A similarities ratio is perfect square. It's going to be the area ratio, right? So that being said, we see EF is parallel to BC. So your triangle AEF is similar to a triangle ABC, right? Then you can have AEF's area, ABC's area is going to be AF over AC's perfect square. Is it right? AEF is 1 minus x divided by 2. ABC is 1. As long as you see the similarity, you automatically use the similarity ratio's perfect square. It's going to be equals to the area ratio. As long as you're done for that, how can I deal with this AF over AC? I don't like AF over AC, right? Because on the right-hand side, I already see 1 over x divided by 2. If I can replace AF over AC into something like x, I will be able to solve the problem right away. So the $1 million question is, how can I replace AF over AC? I have already used the similarities ratios, perfect square, blah, blah, blah. The other part is probably going to use the height. How can I use the height to solve the problem? AF over AC. Is it kind of, I can also use some area ratio to represent AF over AC. AF over AC can be converted into the area ratio between two triangles. If I could, then I'll be able to solve the problem fairly quick. How can I do that? Okay, tell me. Who can tell me? AF, I'm going to highlight it for you. AF, oops, over AC. Can I use some triangles area to represent these two segments ratio? Because as long as I do that, I'm going to replace everything using X. I'm going to have one equation, only one variable, good to go. What is that? AF. Can you find the two triangles? They are kind of sharing the same height. So, but the bottom is one is AF, one is AC. And then the area ratio would be those two triangles area ratio. I'll be asking for Luis.
Can you hear me?
Yeah, go ahead.
AF and AEC.
AEF and AEC, right? Exactly. You can just basically check these two triangles. I'm going to use the color black. One is this black one. The other one is, I don't know, maybe you use yellow. And this yellow one. These two triangles, they're sharing the same height, right? And the area ratio would be AF over AC. That's it. So what is AF over AC? Will be the area AEF, area AEC, right? Of course, a perfect square. This is going to be here. AEF over AEC. What is AEF? AF is 1 over x divided by 2. AEC is actually 1 over x divided by 2 plus x. So this guy take a perfect square, right? Now the following part is fairly straightforward. You just want to say this guy equals to this guy. Do some quick algebra manipulation. You get a value for x. X equals 2 root 5 minus 2. You see, it's a fairly easy problem, right? As long as you see triangles area problem, start with the definition. This problem you can't use the definition. Second one will be the ratio. Either the height, bottom, this kind of ratio, or using the similarity ratio. This is, trust me, most of the area problem, you're going to use such approach to solve it. So far, so good? If all good, let's go to another problem. Second problem will be exactly the same thing as this problem. Just try to use the ratio to build up a relationship between different triangles, and you are good to go. Question number 2. Given triangle ABC, DE are both midpoint of AC and BC. BF equals to 1/3 of AB. Try to prove two things. First, try to prove GE is parallel to AC. Second, try to determine the ratio of triangle BFG to triangle BEG. I'll give you the graph. The graph goes like this. I'll use the color maybe black. Oops. This is okay. 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 So this is going to be my A, B, C, D, E, G, F. Okay. So I have a triangle ABC. D and E, they're both the mid of AC and BC. I'm going to use this, right? As long as you see mid, you basically use a denotation to basically, okay, list them out. Okay. And BF is not a mid. BF is only 1/3 of AB. Okay. With all those information, try to prove first GE. You do a connection between the intersection, right? G to E. GE is parallel to AC. That's the first. Second thing is try to determine the area ratio of BFG, the green one, to BEG. BEG is the yellow, is like the red one. Okay, first thing first. Let's go to the first problem. GE parallel to AC. How can I prove GE is parallel to AC? The thinking process is very important, right? If I proved GE is parallel to AC, then what's going to happen? The question only tells me E is the mid of BC, right? If one day GE is parallel to AC, then G must also be the mid, right? G must also be the mid. If G is the mid, I need to put G into a triangle to prove it is the mid of the triangle. At this moment, G is actually in triangle BAD. By any means, G is not the mid of any segment. Is there a way that I can create a triangle and make sure G is kind of the mid of the triangle? The thinking process is very important, right? If I want to prove GE is parallel to AC, then G will be mid of BD. That's no problem. But I need to put kind of like G into a triangle to make sure, G is the mid of BD, but also I have a triangle thing. At this moment, the G is in the ABD. G is the mid of BD, no problem. But I don't think you really can't use any parallel or something like that, right? You have to think about it. How can I put G into a certain triangle and make sure G is the mid of one side? This is the thinking process, right? And also, there's another very nasty condition that BF is 1/3 of AB. I like mid, right? But I do not like 1/3. Is there a way for me to get rid of this 1/3 thing? Or, 1/3 doesn't make sense, right? I want to make everyone is the mid. How can I put all those unmids together and solve this problem? You're probably going to construct a triangle and make sure G kind of like work good for that, right? So whenever I say construct a triangle, you're probably going to use some auxiliary line to make it happen. Like I said, if G is, my goal is try to prove G is the mid want to show, number one, right? Want to show G is the mid of BD. How can I prove G is the mid of a PD? Yeah, I see Ethan have some ideas. I'm going to ask for Ethan. What's that?
I was thinking because it's 1/3, in order to make it 1/2, you could just put a midpoint in between like F and A and then connect that to C so that you would have a triangle where you have midpoints all throughout.
Is that right? That's a brilliant observation. Why? There are so many factors indicating you have to put a H. First, you don't like this 1/3 thing. But as long as I find the H is the mid of AF, BF equals to FH because BF equals to FH because to HA, then you could probably create a lot of like a mid, right? And let's have a look. As long as I do a connection between HD, I was trying to put a G into a mid of a triangle. So for now, if you check the triangle BDH, that's going to be exactly the triangle what I'm looking for. Exactly triangle what I'm looking for. So I can do something like this. Find the midpoint of AF, which is my H. And then connect HD. Let's have a quick look. This is going to be something so easy because you have AH equals to HF, right? H is going to be the mid of your AF. AD equal to DC. So therefore, HD will be parallel to FC. HD will be parallel to FC. That makes sense? Okay. Because BF is the same as FH. BF is the same as FH. And HD is parallel to FC. So therefore, BG is the same as GD in triangle BHD. Does it make sense? Does it make sense? BG is going to be the same as GD. And then the following part will be given because the question also tells you what? BE is the same as EG, is the same as EC. So GE is parallel to AC. QED. You see? Only a couple of lines, you get what you need. Does it make sense to you guys? Right? This is something quite understandable. Why you want to find out the midpoint? Because you see this nasty 1/3 thing. You do not like 1/3. What is the best way to get rid of it? Just find a midpoint of your AF. So your BF, FH, AH, they're all the same. So therefore, you can find out GF is parallel to HD. And taking from there, you get whatever you need. This is a fairly understandable stuff. Does it make sense? Make sense to you guys? Yes or no? Can I have some feedbacks? Are we all good? It's fairly understandable, right? Yeah, just try to use the hint given by the problem, and you'll be able to solve the problem by itself. Okay. If all good, let's go to the second part. Let's try to determine the area ratio between the green one and the red one. Well, the green one and the red one, those two triangles, they're not sharing the same height, for sure. And they're not sharing the same bottom, right? Yeah, you can say they're sharing BG, but if you say they're sharing BG, oh my God, the two height will be totally like this, right? This is crazy. So there's no way for you to do the 1 over 2 times, bottom times height, so on and so forth. So that being said, maybe I have to do some trick in order to figure out what is the what is the area between the two. So if you can recall, there are how many ways to determine the area ratio? Number one, using the definition. I don't think so you can do that, right? You don't know the bottom, you don't know the height, you don't know nothing. Well, the second one is using the ratio. Well, the ratio, like I said, one is a similarity. Yeah, there are similarity in this triangle, but I don't think the green one, the red one is similar to anyone, right? They're kind of like a very strange triangle, like whatever. Well, the only way for you to do the similarity, the only way for you to do the ratio is more like using the height, using the bottom, so on and so forth, in order to make it work, right? Actually, that's a very worth trying part. So how to do that? I'm gonna make the graph one more time. Let's try to determine this. Determine S BFG S BEG. BFG and BEG. I'm gonna take the graph one more time. Okay, maybe I'm just gonna manually draw it. A, B, C. Here, it's 1/3. Okay, your F, your G, your E, your D, right? You want to determine the green one is here and the red one is here. Like I said, there's no way for me to do it right away, right? I just want to find out the ratio, some ratio relationship, so on and so forth, and I would be able to make it out. But how can I find out the ratio for the green one and the red one? I think it's kind of challenging because they're not really connected to each other. So let me try to do a workaround. If I can find out the ratio from the green one to, I don't know, to another triangle, maybe the big triangle, and then I find out a ratio from the red one to another one, maybe the big triangle. Taking from there, maybe I would be able to solve the problem. I don't know, I'm just curious. Maybe I would be able to solve the problem. Okay, so finding the ratio, sometimes you need to have kind of like in physics, right? You need to find out like a reference, right? Which one is moving. It's the same thing for mathematics. You need to find a reference. Maybe ABC, the big triangle, is a reference. Find a reference. What is a reference? I don't know. Maybe ABC, maybe something else. If I find out a ratio between my green one and the big reference, my red one, the big reference, so my work is done. Let's focus on the first one. Let's try to find out the reference from the green one to the big one. I don't even know what is the reference, but let's have a look at it. Try to make my life easier, if my triangle BFG, the area is A, for instance. If this is A, how can I gradually find out the big triangle ABC's area? Who can tell me? You know, whenever you do the ratio relationship, right, you can't directly from A all the way to the entire ABC. You must be doing something gradually. Maybe find a triangle at like the green triangle's area and then find its neighborhood area. And then find it like the next neighborhood area. And maybe like the guys across the street area, all the way to the big area. You can't just do everything at one shot. Who can tell? How can I gradually find out this kind of like an area relationship between the green one and the big one? What is the neighbor for triangle, for the green triangle? It basically have two neighbors. One is the red one, of course, but the red one is the one for you asking you, right? If you know it, there's no need to do it. So you can't find out the ratio from the red one, right? That's the one you need to prove eventually. Then let's try to find other neighbor. The other neighbor is the quadrilateral FGDA. But like I said, most of this quadrilateral triangle, most of this quadrilateral problem must be converted into triangle, right? You're more familiar with triangle. You're not familiar with quadrilateral. Then what can I do to cut this quadrilateral into a triangle? Who can tell me? Every single step, there's a rational, there's a reasoning. You're not like random, okay, because I have the answer. Let me try to read it, do this. No, there's a rational for it. Paul.
Connect AG.
Connect AG. That's brilliant answer. As long as you connect AG, the neighbor of this green triangle will go to triangle AFG. Who can tell me? If the green triangle has area A, what's the area for AFG? They are sharing the same height. So the area ratio will be the bottom ratio. So what is the area of AFG? What is F? F is 1/3 of your AB line, right? Don't forget, BF is 1/3. So the area of AFG is going to be, who can tell me? Oh, this is easy. Paul?
2A.
2A, right? That's brilliant. Okay, let's continue. Like I said, you're going to go to your neighbor, your like the next neighbor, or cross the street all the way to the entire community. If this is like A and 2A, so that being said, I'm going to use the color maybe green, okay? So my triangle AGB is going to have area 3A. Then what's next? What is the next triangle I need to touch? Your neighbor. Your neighbor. What is your next neighbor? The other students? I want everyone to get involved into our discussion, right? Not only 1 or 2 students. I have, like I said, you're going to go to your neighbor, your next neighbor, your comparison is getting bigger, 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 bigger. You go to A from the green one, you already go to the AFG. Now you know the area of ABG. So what's your next neighbor? Your next neighbor is going to be ADG, right? Let me use the color. The yellow one, right? You're getting bigger, bigger. Because your G is the mid. Still remember? You just proved. G is your mid. So therefore, ABG and ADG, they have the same area. So if this is 3A, this is going to be 3A. Now you kind of know your triangle ABD has area 6A. So what's next? What is your next neighbor? How to know that AFG is 2A? Because AFG triangle and the BFG triangle, they share the same height. And the bottom one is BF, one is AF. F is the 1/3 point of AB. So the bottom ratio will be, 1 or 2. Now you know ABD's area is 6A. D is the mid. So therefore, your entire ABC's area is going to be what? 12A. Does it make sense? Oh, so that being said, your triangle BFG over your triangle ABC is going to be 1/12. So therefore, BFG is 1/12 triangle ABC. Like I said, you're trying to find out a reference. It looks like ABC is a reference. right? If all good, what's the next step? I'm already done for my triangle BFG. So next time I'm going to do the triangle B like the red one, right? I'm going to write it one more time. The thinking process is exactly the same. A, B, C. Okay, F, E, G, D. Okay, now let's focus on this red triangle. Who can tell me what should I do to find the red triangle already? What I need to connect? I'm already done for the green one, right? I did a connection between AG. Now let's deal with the red one. What should I do for my red one? I'll be doing exactly the same thing. I want to start with the neighbor, and then a further neighbor, and then to the community, cross the street all the way to the community. This guy has two neighbors. One is the green one, of course you can't touch. The other one is EGC, right? Can I do this EGC thing? Oh, who can tell me? Paul, can you tell me what should I do?
Same area.
If this is B, this is B. If this is B, my BGC is going to be B, right? So what should I do next? What should I do next? I need to all the way go to the entire community, right? What is the next neighbor? Jonathan?
GDC.
Is that right? You just find your neighbor. This is not rocket science. GDC is going to be 2B, right? Okay, what's next? Entire BDC is going to be 4B, right? If entire BDC is going to be 4B, so what's the total area? What's the total area for the last one? Find your neighbor, your next neighbor. My black triangle's neighbor is who? And then how to get to the entire big triangle. Every single step, there's a rational behind it, right? What's that? It's going to be my triangle ABD, right? Yes, ABD. I think Jonathan has the correct answer. That's going to be 4B as well. So my entire triangle ABC is going to be what? 8B. 4B plus 4B. So my triangle BGE over my triangle ABC is going to be 1/8. So my triangle BGE is going to be 1/8 my triangle ABC. Now you have find your reference. I'm going to use the two color. My green one is 1/12 of the entire triangle ABC, while my red one is 1/8 of my triangle ABC. So the area between BFG, BG is going to be what? 2/3. That's it. You see, this is like a common strategy what we keep using the ratio to determine the area. How to use the ratio? Always either similarity. This problem does not have too many similarities, right? Because this weird two triangles, no one's similar to them. Second is basically use the height, the bottom, right? Same height, area ratio will be the bottom ratio. Same bottom, area ratio will be the height ratio. You just keep moving. The most important thing, you need to find a reference, right? The green one and the red one, they all go to the same reference. So at the end of the day, they're going to have the same exactly the same area ratio. See, this is a very understandable thinking process. Does it make sense to you guys? Can I have some feedbacks? Yes or no? Can I have some feedbacks? It makes sense, right? So that means like in the future, as long as you're doing any similar triangle, blah, 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 related problem or area related problem, try to find out a ratio. Picking from there, you'll be able to solve the problem. In today's assignment, I'm going to use exactly the same strategy. You're going to find out a ratio from the smaller one all the way to the big one, and then find out the relationship between them. So far, so good? If all good, let's go for another problem. Let's go for AIME problem. It's a fairly old AIME problem, but I think it's still very interesting. Yeah, it's this problem from it's 1989. It's a fairly old problem, but it's AIME question number 15. This last AIME problem. So let's have a look. I think still valuable for our discussion. So P is inside a triangle ABC. Line segment APD, BPE, CPF are drawn with D on BC, E on AC, F on AB. Okay, there's nothing saying, right? There's nothing special. AP equals to 6. BP equals to 9. PD equals to 6. PE equals to 3. CF, the big one equals to 20. Okay, so like the entire one equals to 20. So I don't really write it. I'm just basically putting it down. With all those information, the question asks you to determine the area of triangle ABC. Okay. You give me some random lines, right? I don't even know like where this P comes from, right? There's just random some lines, okay? They're intersecting with each other, blah, blah, blah. You give me some lengths. You gave me AB, like AP, PD, PB, EC, EP, and you give me CF. You give me the total length of CF, but you didn't tell me CP reaches PF, right? But anyway, with all of this, you wanted me to determine the area of ABC? Determine the area of ABC. I don't even know the height. This problem, I think the height is difficult, right? The bottom, the height, the angle, there's nothing for me to determine the area, right? Like I said, step number 1 is always using the definition, the bottom, the height. There's no bottom, no height. Step number 2, using some ratio. Using some ratio, I need to have some triangles area before I can go for the ratio thing, right? If I know nothing, how can I determine the ratio? But it looks like I really have no idea about the bottom, about the height. I kind of, maybe I need to determine something and then be able to get the area of certain triangles and taking from there to get a ratio. I don't know, I'm just curious. Well, as long as you see such a problem, what can you do? I don't know, I'm just curious. What can you do? Like I said, I know AD segment, AP, BP. For AD, I know AP, PD. For EB, I know EP, I know BP, right? But only thing is for CF, I only know CF itself, but I do not know CP and BP, right? So even though, I mean, if I'm an OCD, right, I really feel very uncomfortable, right? I really have to figure out what's the value. I mean, what is the value for this like CP, CB, something? Or I have some other stuff I can deal with. Okay. I see somebody have some question. Somebody have some ideas. Let me try to ask you one by one. Maybe like Eric, you have some comments? I think Eric mentioned a very good comment.
Since you have F on AB, can you use the Stewart's theorem?
F on AB, okay. I can use a Stewart for ridge triangle. So my Stewart goes like this. This is my Stewart, right? 1, 2, 3, 4, 5. As long as no 4 of them, I'll be able to determine the 5th one. So which one do you think I can? Ridge triangle, I can use Stewart.
Maybe ABP.
ABP, okay. ABP, now I only know 2. I only know AP and BP. I don't know AF, I don't know FB, I don't know BPF, right? But I think it's a good idea. I think because he mentioned, Eric, think about something like Stewart, okay? We're probably going to use a Stewart in this problem, maybe. Yeah, that's a very good try. Okay. What else? Maybe Luis.
Oh, well, you can look at triangle ADB.
ADB, okay.
Oh, actually, now I'm looking at it. Okay, first of all, you can see ADB, and then you can see that BP is the bisector, or not bisector, like it cuts the line, it cuts the base into equal distance.
Okay.
Yeah, and then also if you look at AEB,
okay.
like there's a ratio on that, but I don't know if it's going to be useful. But I feel like since you know, oh wait, CF is not the height. Never mind.
Yeah,
Well,
CF is not a height, and BP is not necessarily the angle bisector. It just cut it into 2 equal parts.
Well, is it median then? What's it called? I forgot what's it called.
Yeah, it's a median. Median. Yeah, it's a median.
Wasn't there a rule on the median?
But again, if you're talking about a triangle ABD, you have 2 sides you don't know, AB and BD, right? You have to make sure you know 4 of them before you can determine the last one. Is that right? Like the median height, it's also coming from the Stewart. The Stewart asks you to have 4 out of 5. So even the median cannot really save you one side, right? But that's okay. It's also a very good observation. So let's go to Bolin.
I don't know if this is gonna be useful, but I think we can find AB. But
AB, okay. What's the value for AB?
wait, no, I just realized it is APB.
APB, okay.
A right triangle, a right angle.
No, I don't think so. At least I don't know, because the question doesn't really tell me.
It doesn't make sense what I'm saying.
It still makes sense. It's just like trying to thinking, right? It's a searching process. Yeah, I think every student try to get involved. That is perfect. It's a discussion process, right? So this yeah, I think Luis, you have a new question? Yeah.
Wait, are you able to divide the triangle into like AEB and CEB?
Okay.
And I don't know, since they have this okay.
But you don't know AE, you don't know EC. So that's the problem. So this problem, yes, go ahead.
Since the other one is it's 3 and 9, and I don't know, I just want to do something with 3 and 9, and I
that's
think
a brilliant observation. Yes, that's a brilliant observation. Yes.
But can we make wait, I forgot the name. Can we draw a line from E to D?
From E to D, okay.
Yeah.
Then
and make
yes.
Yeah, like a trapezoid.
Trapezoid?
Yeah, and wait, and then we know the 2 diagonals, right? So
okay, you think they are cyclic?
You know, like the butterfly. The
butterfly?
Yeah.
Okay, yeah, I know the butterfly. But butterfly is okay. That's gonna help you to determine the area?
No, I don't think so.
Yeah, because and also like the diagonal AD and EB, they're not perpendicular, right? If they're perpendicular, like the entire thing is so easy.
Yeah.
Okay. Yeah, it's okay. It's a very nice thinking process. Yeah.
Can we say can we do something with the area with 3 and 6 because they're a ratio? They
The
share a
area
height.
3 and no 3 and 6 is not areas, like two
No, I
two
meant
segments.
can we just make a claim where it's since EP is 1/2 of PD,
Mm-hmm.
triangle CAP is 1/2 of CP.
CAP, okay, is 1 or 2 of what?
CPB.
Yes, of course.
Okay.
CAP is 1 or 2 of CPA, right? CPA.
Yeah.
Okay. Yes, that's good. Yes. But you don't know the area, right?
Hold on.
Okay,
hold on.
I think like everyone has a very nice discussion. Yes. So this is like a tricky part of this problem. You don't really know the side, the 3 sizes, AB, AC, BP, like BC. You only know this kind of, I don't even know, this is like what? Like the internal AD, B, CF. How can you wipe smartly using them? This is the challenging part of this problem. Okay, how to solve this problem? I think Louis actually mentioned a very important thing. You see, I'm just gonna remove this there. So this problem, you see, sometimes you need to be very sensitive about the numbers they gave you. They gave you AP, PD. This is kind of like equal to each other, right? P is the mean of AD. And then they give you a P and BP. EP is kind of what? 1/3 of EP. Is this something similar as our question number 2? As long as you see 1/3, you don't like 1/3, right? If you can do some magic, create some midpoints, right? And taking from there, maybe you will be able to solve the problem fairly quick. Like I keep saying, you know AD. I'm going to use the thing here. You know AD, and to more specific, you know AP and PD. You know EB, and more specific, you know EP and BP. But you only know CF. You do not know CP and BP. It's like CP and PF. CP and PF. So that being a CP and CF, PF. This part you have no idea. Is there a way for you to do some magic, even figure out a value of CP and PF? Hopefully taking from there, you can solve your problem. Right? Let's have a quick look. I don't know, I'm just guessing. Let's have a quick look. How can I make this happen? Of course, I'm going to make some auxiliary lines. I'm going to do something like this. From D point, I want to make what? DQ parallel to AB. Okay. Another one is DM parallel to AC. Why I'm doing this? Don't be mad, okay? Why you're doing this? Later you're gonna find out I'm doing this for a reason. Okay, let's have a quick look at it. How are we gonna deal with that? Check out this triangle. I'm gonna maybe zoom it like a little bit. The green triangle and the green triangle. Triangle APE. Triangle DPM. These two triangles, even though my graph is not so good, but these triangles are congruent to each other. Is that right? Do you guys have any objections for that? APE, DPM. these two triangles are congruent to each other? Yes or no? Can I have some objection? Yes or no? Okay. If this is congruent, here is 3. Here is also 3. So I'm going to say EP is the same as PM equals to 3. Okay. If that's the case, my PB entirely equals to 6. PM equals to 3. So therefore, MB equals to 6. Does it make sense? MB equals to 6. So therefore, M is the mid of EB. M is the mid of EB. Does it make sense? Okay. M is the mid of AB. DM is parallel to AC. So therefore, D is the mid of CB. D is the mid of CB. Okay, D is the mid of CB. QD is parallel to AB. So therefore, Q is the mid of CF. Okay, this is brilliant. You see the number. M is the mid. D is the mid. Q is mid. Okay, everyone is the mid. You see, in the math competition, when the numbers are given to you, this number is not given for fun. There's a ration, there's a reason behind it. You see? Now you find, okay, M is the mid of EB. D is the mid of CB. Q is the mid of CF. Everyone is the mid. Is it right? Okay. Okay. If that's the case, let's have another quick discussion. Q is the mid of CF. Let's have a look at about these two triangles. I use the color blue. These two triangles, triangle QDP and the triangle FAP. These two triangles, they're also congruent to each other. Do you guys agree with me? Yes or no? These two triangles, even though, again, even though like the graph is a little bit nasty, but these two triangles are also congruent to each other. Do you have any objections? Yes or no? Can I have some feedbacks? Are we on the same page? QDP and FAP, they're also congruent to each other. Why? Because AP is the same as PD. Can I have some feedbacks?
Yeah.
Okay. So if these two triangles are congruent to each other, I will find out another thing. E is also the mid of QF, right? P is also the mid of QF. Like I said, everyone is mid, but now I have some rational. P is the mid of QF. Q is the mid of CF. CF equals to what? CF equals to 20. So that being said, I finally get what I want. QCQ equals to 10. This is 5. This is 5. CQ equals to 10. QP equals to PF equals to 5. Any objections? Yes or no? This is understandable, right? Now, I think I'm almost done. I would be able to determine the area of this entire triangle ABC. Why I'm saying this? Of course, I have no idea about the angle, the height, blah, blah, blah. But let's have a quick look at it. I'm going to focus on these triangles. Let me try to use the color maybe red. The triangle CDP and the triangle DPB. These two triangles, okay, first, I don't know what is the area of this. Let's put it there, okay? If for some reason I figure out what is the area, first of all, I know these two areas are the same because D is the midpoint. Is that right? D is the midpoint. As long as I figure out one of them, I use the value multiple 4, I'm going to be able to figure out the entire triangle ABC's area. Does it make sense? Does it make sense? Because CDP, DPB, APD, and APC, those 4 triangles, they have exactly the same area. I'm going to say this. Because triangle CPD area, same as DPB's area, same as APB's area, same as APC's area. They're all sharing either the same height or the same bottom, right? Because everyone is mid, so the bottom is always the same, right? The height, you can basically see that. So therefore, my triangle ABC's area is 4 times of my triangle CPD's area. So the $1 million question is, how can I determine triangle CPD's area? I'm going to put it here. How can I determine triangle CPD's area? Who can tell me? Triangle CPD's area. Paul.
Maybe you can use like Heron's formula and then like solve using algebra for like the unknown value of CD.
You guys follow him? That's a brilliant answer. Solution number 1. I'm gonna take a screenshot. Okay, this is our last screenshot. Is here. Whoops, no, can't remember. Yeah. It's actually upside down. So, oops. So yeah, everyone see my password, right? Yeah, that's okay. Here, take a screenshot. So let's drag it into another page. Let's try to see how we're going to do this. This is our last problem. We're going to make it fairly quick. So how to determine this? Insert image, photograph. There you go. Zoom in a little bit. Okay, solution number 1. Like Paul mentioned, let's try to do some quick algebra. Why? Because let's focus on these 2 triangles. This triangle CDP is the same as the triangle BDP. Right? And they have the same bottom. You can use the Heron's formula for triangle CDP. You already know the size. One is so I'm not gonna just directly write it. I'm just gonna give you a quick hint. For this triangle, CDP, you already know CP equals to 15. CD is X, I don't know. BT, 6. You can use the Heron's formula, right? To determine the area. Hey, the other one is BPD. D, B, P. This is X. PD is 6. PP is 9. You can use your Heron's formula in order to have this nasty under root, blah, 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 equals to blah, 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 blah. And then you can determine the value of X. As long as you know X, you would be able to find out the area of CDP and taking from there, solve the problem. Do you guys follow me? Yes or no? Can I have some feedbacks? Yes or no? It's understandable, right? Okay. Do we have something even easier? Solution number 2. Solution number 2 is just what Eric mentioned. We can actually, instead of use, this is going to be a lot of crazy calculation for sure, right? Solution number 2, we can actually use the Stewart theorem to directly solve it out. Where I need to use my Stewart? I'm going to use my Stewart here. Look, this is my Stewart in triangle CPB. You already know, I'm gonna zoom it like a little bit, right? C, B, P. This is X, this is X, this is 6, this is 15, and this is 9. You can use your Stewart, right? Stewart said, as long as you know 4, you can basically calculate the other fifths, like the last one. Now, this is already like in a, they have like a mid, right? Because D is the mid. So you basically, you can have this equation right away. So using Stewart, you can directly determine X. So either way, using Heron's formula or using the Stewart, you will be able to solve this problem fairly quick. Are we all on the same page? Yes or no? Can I have some feedbacks? Yes or no? All right. Yeah, that's pretty much what I want to say for today's lecture. This is our lecture number 1. Okay, we talk about the area method. Like I said, most of the time, you won't be able to really calculate the area using the height, using the bottom. That's too naive. Most of the time, you're actually using the ratio to do the calculation. Ratio, there are 2 ways, either using the similarity. For this problem, there's no way to do it. Or most of the time, you're actually using this height, bottom, ratio, blah, 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 transfer from here to there, all the way you figure out the calculation. Okay, in our homework, we're going to give you something similar. You can use this technology to see if you really understand what I'm talking about. And in the next lecture, we're going to talk about something, how to use, we still have some other ways, right? This is the, okay, I'm going to come to here. This is our strategy 1 definition, strategy 2 ratio. We still have some sine law, cosine law, Heron's formula, blah, 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 some more flowery ways. So therefore, we're going to use our next lecture to talk about something, how to use the number 3 and number 3 and number 4 way to do the problem. Yeah, Luis has a question. What is the number again? What is the question? Is 1989 AIME question number 15. All the numbers, he said the numbers are really nice. Yes, all the numbers are given for a reason. There's nothing just random numbers. So you need to really scratch the surface and dig out the essence of this problem. Sometimes you need to have some sense. You know, a lot of times they give you the numbers, they can automatically form a equilateral triangle or like a right triangle using the reversed Pythagorean theorem. So try to be very careful about the numbers. All the numbers are specially designed to help you to expedite your calculation. All right, I think we're running out of time. Lecture number 1, I'm always going late. Sorry about that. And I really want to give you as much information as possible. Hopefully you guys enjoyed today's lecture. And we're going to upload assignment into our Google Classroom. And then I'm going to talk to you guys for the next week. All right, bye guys. Have a good one. Bye.
Bye.
Bye-bye. Ciao, ciao.